3. All good? All right. Hi, everyone. I'm going to give a very basic introduction to two very basic concepts from category theory, because they will be useful for my talk and also for Chris's talk. Please interrupt me if there's any questions. Very abstractly, category theory is a very abstract language to talk about a lot of things in mathematics and also in the real world. And I think it's very exciting, a very elegant way of describing things. And it's very much about describing things by how they relate to other things, vaguely put. And I hope to make that a bit more concrete in these few minutes. So let's start with something we all know, functions of sets. If we have a function f from a set x to y, we can write that as f from x to y. And if we look inside of this function, we see that x has some elements, y has some elements, and what f is a choice of element in y for each element in x. So far, so good, I hope. One of the nice things we can do with functions is compose them. So if we have another function g from y to z, and we also have assigned for each element in y an element in z that g maps to, then we can compose these functions to get a function g composed with f that takes us from x to z. And what is that? Well, for each element in x, we look at where does it map in y, and then through f, and then where does it map to z by g. So far, so good, very simple. We can also think of this slightly more abstractly. We can think of these functions as arrows or morphisms from a thing called x and a thing called y. And we can think of how these morphisms between these objects x, y, and z compose with each other. And we can do that without looking inside the boxes of x. We just think of this as an arrow from x to y, and the only thing we care about is what the compositional structure of these arrows is. By doing that, we don't have to define how f works on all the elements of x. We only look at composition. And I'm going to claim to you that by doing this in this abstraction, no information about f is lost. Because we may, and the argument is the following. So imagine we pick an element, a set of one element. Let's call that y, and the unique element in it, we call it star. Then we can look at all the functions from this set I to x. And what does it do? Well, we look at such a function that's called a. We look at which element in x does it point to. And well, that's one single element in x. The set of functions from I to x is equivalent to the elements of the set x. So we can talk about elements without ever looking inside of the boxes. We just discuss the kinds of functions that exist between sets. Now, if you were to compose, does this work? Does it have a laser? No. So if we compose such a function with a function f, what do we get? Well, we first get where this function from I points to, and then we apply f, and that's exactly the same as the element we get, because any composition also from I to y is equivalent to an element of y, and the element we get is exactly the element that this function points to, and then we apply f. So in other words, the function f is fully defined by how it composes with different kinds of functions from I to x. So we don't need to talk about the elements of x. We just talk about how f composes with other things, and that tells us everything we need to know about the function f. So that is kind of an idea here that we're going to apply. We're not going to look inside of the boxes. We just think about compositional structure. And this compositional structure in this particular case satisfies two very useful axioms. The first is associativity. So if we have a function G from U to X, F from X to Y, and H from Y to Z, then we can first compose these two and then apply H, or we can first apply G and then apply the composition of these two. And for sets, luckily, that's always satisfied. The second axiom we have is an identity axiom. Namely, every set has an identity function, which just maps every element to itself. And if we apply first the identity on X and then F, that's the same as applying F. Or if you apply F and then the identity on Y, that's the same as applying just F. So this is an associativity and an identity axiom, and functions luckily satisfy this. So this brings us, if we try to generalize this from functions on sets to something more general, brings us to categories. So a category is simply a set of objects here, such as X, Y, and Z. And for each pair of, and here X, in the case of functions, represents a set. For each pair of functions X and Y, a potential set of maps between the two objects in a way that we can compose these maps. So if we have an object X and object Y mapped between by a function F and a function G that maps to Z, then we have some composition from X to Z. And that this satisfies identity and associativity rules. So this is a very general construction. I haven't said that we're here talking about functions that map between sets. This can be, these objects can represent a whole lot of different things. And but a concrete example is the sets that we saw, where every X here represents a function, and a function, and the F here will be a function between sets. And so now we no longer think of these X's as representing sets, but we think of them as abstract objects. So we just think of a category as some set of abstract objects with some arrows between them. And I will interchangeably call them arrows or maps or morphisms. So there's a lot of kinds of categories that we can discuss, and a couple we've already seen. So we have seen the category of set. Its objects are sets, and its morphisms are functions between sets. We can think of the category of vector spaces, whose objects are vector spaces, and morphisms are linear maps. We can think of a category of matrices, whose objects are natural numbers, and whose morphisms are matrices of that shape. So a morphism of n to m would be just a matrix from n to m dimensions. We can think of topological spaces and continuous functions. We can think of, and that's a lot of what Marie said. We looked at different kinds, arguably what we did, we were looking at different kinds of categories. We talked about the categories of topological spaces, sorry, of topological manifolds, that's a category, and its maps are, its morphisms are continuous maps, homomorphisms. No, they don't need to be isomorphisms. Anyway, so we can have a whole a group of things. Or groups, its objects are groups and morphisms are group homomorphisms. But that's not all a category can do. There's also things that themselves, that we know in mathematics, but that themselves are categories. So this is not a category of something like a set and something like a function. And one canonical example is a preorder. So a preorder in the classical definition is a set with objects, so objects A and B, and a potential relationship that A is smaller or equal than B. And we require that this relationship is reflective, so that A is smaller or equal than A, and transitive, that A is smaller than B is smaller than C, then A is smaller than C. So we can draw a preorder, but as a diagram where we draw the objects and potential smaller and equal relationships between them. And an example of this is the integers, and smaller than equal will be just the ordering of the integers. Now we can also write a category that is equivalent to this preorder. Namely, we write down a category whose objects, set of objects, are these elements P, and the smaller than equal relationship becomes an arrow in this category. Now you'd see that a category that has at most one arrow between any two objects is equivalent to a preorder. This works because the reflexivity gives us an identity arrow from A to A. The fact that we have a transitivity means that we can compose the morphism from A to B and the morphism from B to C to get a morphism from A to C. And associativity is trivial because, as we said, we have at most one morphism between A and B because the smaller or equal relationship is just that. Something is either smaller or equal or it is not. There's no way you cannot be smaller or equal in two different ways. That's why there's only a unique morphism. So any composition between arrows is equal, and thus associativity is trivially satisfied, and thus preorders are categories with at most one arrow. Any questions so far? Yeah. Yeah, that's a very good point. That's the difference between a preorder and a partial order. In a preorder, things can be equal in the sense that the one is smaller than the other and the other is smaller than the first, without being identical. Whereas in a partial order, and for example, the integers are partial orders, things can be smaller and equal than each other without being identities. So you can have cycles, and that just, so a category language, that means that they're isomorphic, that there's an arrow and you can go back and that's equivalent to going into a circle. So it's a bit like different groups can be different shapes can be isometric or have the same shape without being identically the same. But that's a bit of a semantic discussion. Does that answer the question? Okay, thanks. An important example of a partial order, and that we can consider the category of something, is given a topological space, we can have a category of open sets. And the objects are open sets, and the morphisms are subset relationships. So if an open set U is smaller than an open set V, then we write that as an arrow from U to V. And this would be also a preorder. And this can be used to define sheaves. We can also think of a group as a category. So not a category of groups, but one group as a category. A classical definition of a group, you've seen that now, is a set with an associative binary operation with identities and inverses. Now, within a category, an isomorphism is any map from F from A to B, such that there exists any other map from B to A, such that if we compose them in both the directions, we get an identity map. So then, as you can maybe see, to get a category out of a group, we say the category has a unique object. We call that star. And each morphism corresponds to a group element. Then if we have two such group elements or morphisms, we can compose them by the composition rule, and this is equivalent to group composition in the classical formulation. And we have associativity by the axioms of the category and by the axioms of the group. We have an identity morphism, which corresponds to the identity element in the group. We require that all morphisms is an isomorphism in the group theoretic sense, meaning that it has an inverse. So here we can see that any category with a single object and whose morphisms are all isomorphisms, meaning they have inverses, is exactly equivalent to a group. So here we can see that a lot of things that we care about in math have a very elegant description in terms of categories, I feel. Another fun example is the path category. So if we have a topological space X, then we can consider the category of paths. Its objects are points, so these are just elements of the topological space, and a morphism from X to Y is a path from X to Y, which would mean that we have a map from the time interval from 0 to 1 to the manifold. So they would describe a continuous path, such that the starting point is X and the final point is Y. We can also compose these paths by just saying, if we have a path from X to Y and a path from Y to Z, we say that the first half of the time we traverse from X to Y, and the second half of the time we traverse from Y to Z, and it gives us a path that also between time 0 and 1 walks all the way from Y to Z. So this allows us to compose a path. But actually, this is not associative, so this would not have been an example of a category. Why? Well, if we think of a path, if we think on the real line of a path from 1 to 2, a path from 2 to 3, and a path from 3 to 4, if we first compose from 3 to 4, and then with 1, we go faster through the first part. And if we would first compose the second, from 1 to 3, then we would go faster through the second part. You can see this in a diagram I tried to draw here. So there may be similar paths also going from the start point to the end point, but they're different in time parameterization, so they're not exactly the same. The solution here is to take something called a thin homotopy of paths, which I won't go into detail, but it says something that we can reparameterize the paths, and then we say that they're equivalent. Now we thought of groups as categories, and we know that a map between groups exists, namely group homomorphisms. We can try to generalize this as thinking of a map between categories, and there exists a general formulation for that. I'll try to hurry up. So a group homomorphism between two groups means basically that we take each group element in G, map to a group element in H, such that composition is preserved. We can think of that also in category theory language. If we have two categories, we say that a functor, which is a map between categories, from the category C to the category D, maps between the objects. So for each object in the category C, it gives us an object in the category D. And any morphism in C from A to B is mapped to a morphism of f of A to f of B. And we require that the identity is preserved and that composition is preserved by this mapping. And we can see that if we interpret G and H as categories, that the group homomorphism becomes a functor because both have a unique object called star, and we map that to the star. And the preservation of composition is exactly the group homomorphism property. So we've generalized group homomorphisms which work on groups to a functor which works on any category. Examples of functors are if we have two preorders, we can define a monotone map, meaning something that preserves the order. This is equivalent to a functor between the two objects interpreted as categories. We can interpret the group action, which has already been defined, as a functor from the group category to set, mapping the unique object to the set itself and mapping every morphism corresponding to a group element to a map from the set to itself. So here we have another example where a group action has this very elegant categorical definition. It's just a functor from the group to set. Similar for representations, it's a functor from a group to the category of vector spaces. Then I'll skip this, but there's a very nice way in which you can see graphs also as a functor from a simple abstract category to the category of sets. It's very nice, but I don't have time for it. And also we can see parallel transport as a functor from the path category to the category of linear maps. I'll share the slides, but I'm wrapping up now. Another thing that can be very elegantly described in category theory. So this is only scratching the surface. We can talk about the category of categories, if we like. Its objects are categories and its morphisms are functors. We can talk about morphisms between morphisms, giving us higher order categories. We can also talk, one instance of that is talking about maps between functors. And these are called natural transformations and are a generalization of equivariance, which I'll talk about more on Wednesday. And you can also study applied category theory, which is putting things like chemical reactions, electrical circuits, or computer programs also into categories, or causal models. That's not visible. I wrote causal models here. Also as instances of categories, which is an example I'm personally very interested in. If you like all of this, these are references where you can find more. Thank you very much.